This video covers what happens to a current-carrying wire when placed in a magnetic field. We know that forces are exerted on charges that have a velocity within a magnetic field, as shown with the right-hand rule. Electrons have thermal motion. This is when the electrons are rapidly jumping from atom to atom. When this is happening, the velocities are random, and therefore the forces are random, and all the forces point in different directions, and they end up canceling each other out. So this is why a normal wire doesn't feel a force within a magnetic field. But when the charges start to move in the same general direction, like when a current is introduced into the wire, the velocities begin to arrange themselves in the same direction. Therefore, the forces arrange themselves in the same direction as well. So looking at this cross-section of wire, we have three labeled positive charges that have a velocity. Therefore, we know a current is established in the wire. Let's say we have a magnetic field pointing into the page. Using the right-hand rule, we see there is an upward force exerted on all these charges that are moving in the wire. So we can develop an equation to describe this upward force. First, we know that the force exerted on a single moving charge is equal to QVB. Since there are multiple charges moving on a current-carrying wire, we say that the total force exerted on all the charges is equal to N QVB, where N is the total number of charges. Now, we know the equation for velocity is displacement over time, and if we say that the length of the wire that we are looking at is L, we can expand our velocity equation to include the distance the charge is covered to be the length of the wire. Solving for T, we find that T is equal to the length of the wire divided by the velocity of the charge. Now let's look at our equation for current. To find current, instead of looking at the total number of charges that pass through a cross-section of wire, like we did with our current equation when we first introduced it, we can look at the total number of charges that pass through the wire. So we multiply the charge of a single charge by the number of charges. We can then plug in what we found for our time equation above into our new current equation, and we simplify. Multiplying both sides by length, we find that the number of charges times the charge of each charge times the velocity is equal to the current times the length. We can see that this equation we found just looks similar to our net force equation, just missing this magnetic field turn. So we can say that the force on a current-carrying wire of a specific length is equal to the current length times the current times the magnetic field. And therefore, we can say that the force on a current-carrying wire is equal to the current times the length of the wire times the magnetic field. Let's do an example. We have a 0.4 meter straight segment of wire that carries a current of 10 amps. We want to find the maximum force on the segment if it is placed in a magnetic field of 0.5 teslas. So we have our force on the current-carrying wire. The current is 10 amps, the length is 0.4 meters, and the magnetic field is 0.5 teslas. So when we plug and chug, we see that the force on this wire is 2 newtons. Now, let's use the right-hand rule to define the direction of the force. Here we have our wire, and let's say that the current is traveling in the positive x direction. This means that all of our positive charges are moving to the right. Let's say that we have a magnetic field pointing into the page. So our thumb still goes with the velocity, which is going to be the current in this case. Our fingers go with the magnetic field, and our palm shows us the force. So then we apply the right-hand rule. We see that our fingers are pointing into the page, our thumb is pointing to the right, and therefore our palm is facing up. So the force on the current-carrying wire is up.